Welcome back, class, to our second overview, our second lecture reviewing the science and math necessary for chemical engineering, where we'll be reviewing ordinary differential equations. By the end of this class, you should be familiar with identifying whether what is an ordinary and or partial differential equation. You should be capable of solving first-order separable differential equations, solving linear first-order equations, homogeneous second-order ODEs, initial understanding how we can use initial values and boundary values to solve for constants, as well as Euler's method, which is a numerical approach to solving differential equations. First, let's talk about what a differential equation is. So a differential equation is an equation that relates a function to its derivatives. So in this case, we have some sort of change in y with respect to t is some known function. In other words, we know how a variable y changes with respect to t, but not the equation that describes it. So we know what dy dt is, right? But I don't know what y as a function of t is. Okay, so let's take a look and see an example of a differential equation, what you might see in a problem set, right? So you might be given, say, dy dt is equal to 5y, and then asked to provide what is the equation of y with respect to t. Or conversely, we know that dz dx is equal to 5z minus 4x. So tell me what the equation is that is z as a function of x. In terms of a word problem, which is more likely to be seen in chemical engineering, we would get something like water flows into a bathtub at a rate of 5 liters per minute. It flows out of the bathtub in proportion to the volume in the tub at 1 liter per minute per liter currently existing. Find the volume of water in the tub with time. And so given this word problem, we would have to say, okay, we know that the volume in the tub changes with time. We have 5 liters per minute coming in, and we have 1 liter per minute leaving. So I have a subtraction sign, and how much is leaving is dependent on the volume currently existing in the tub, so V. So my final equation that I would then need to solve is dV dt equals 5 minus 1 times the volume. Okay, so now that we know sort of what differential equations are, let's talk about different types of differential equations. So there's 2 main categories. The first one being ordinary differential equations. So these are equations which have one independent variable, include one independent variable and its derivative. So sort of like I showed before, the change in y with respect to time is equal to k times y plus sine of t, right? The only variables in here are y and t. I can also have what's called a partial differential equation, or PDE, and this involves partial derivatives in functions of multiple variables. For example, u could change with respect to time and space. So this we see a lot in diffusion or other transport equations. So the change in some variable with time is equal to some constant times the second partial derivative of that variable with respect to a spatial component. In this class, we're only going to be working with ODEs because solving PDEs is significantly more complex. Okay, so let's talk a little bit more about ODEs and their different types of orders. So the order of a differential equation is how many derivatives exist in its functional form. So a 0th order differential equation is just an algebraic expression, right? I've got, some form of y that's equal to some number of constants and or variables. Right? I have no information about a rate of change. A first order differential equation involves dy dt in that equation. As an example, we have dy dt equals ky plus sine of t. This is often seen as some sort of growth or decay. Velocity is a first order differential equation. Population growth, or for chemical engineering, we see this pop up over and over again in terms of reaction rates. So how is concentration changing with time? In terms of second order equations, this involves a second derivative of our independent or our dependent variable with respect to our independent variable. Okay, so for example, we could have m times the second derivative of y with respect to t plus 4 times dy dt equals equals by, right? Where b is some sort of constant. Right here, this could be acceleration, curvature, oscillations, or what we'll see a lot is transport phenomena. So in fluid mechanics, heat transfer, mass transfer, this shows these second order equations show up. We can also have third order equations where I have the third derivative with respect to y. We don't really see that very much in chemical engineering, so we're not going to cover that. Similarly, we could have any nth higher order differential equation, which again doesn't really show up very much, but the concept show up very much in chemical engineering, so we won't be covering that. Okay, so what we'll see throughout the day is that in addition to solving these equations, we are also going to need one additional piece of information in order to sort of solidify and ground these equations. And so the number of pieces of additional information is equal to the order of the function. So the first order differential equation requires one piece of external information, a second order requires two, etc., etc. Okay, let's take a look at first order differential equations. As I mentioned on the previous slide, my first order ODEs have this functional form. The change in y with respect to time is some function of time and y, where time is our independent variable, right? That's shown because it's on the bottom side of that quotient, and y is our dependent variable. It is going to depend on time. Okay, so this is going to describe how y changes with t based on its current values. The complexity of the equation and its solution depend on what's happening on the right side of this equation. What does this form look like? Okay, I also want to note that obviously it does not have to be y and t. We could have any pair of dependent or independent variables. So z and y, x and q, whatever we want. All right, so within this, we can think about how to solve this based on the type of differential equations. So what this functional form looks like. So the easiest one to solve would be something called an autonomous equation. So this is where my f form only depends on y or t, right? So dy dt is a function of f, is a function of just y, or dy dt is just a function of t. So for example, dy dt equals 3y. We can also have a linear form where I have dy dt, and then I have a function, I have y showing up times a function of t. And then I have something on the right-hand side that's just a function of t. So this could be dy dt minus 7t squared y plus 3t. You see that the y multiplied by anything is linear, right? So even though t is squared, y is linear. Okay? And it's multiplied by t. So that's what's different between this autonomous and the linear systems is we have these sort of t cross y sets. Okay, sorry, functions of both y and t. I can also have a nonlinear set that has a functional form of dy dt is a function of both t and y, where y is no longer linear. So I can look at this example, dy dt minus a 7t y squared equals 3t. This y is my dependent variable is no longer linear because I have that square. Conversely, I could have dy dt is equal to the sine of y, right? Once again, y is no longer linear. Okay, so let's look at some of the approaches to solving these types of ODEs. So if I have an autonomous ODE, I'm going to use an approach called the separation of variables. So let's say we're given dy dt equals k of y, right? K is some constant. All I have to do is move everything such that all dependent and independent variables are on their own side, right? So I'm going to move dt over to the right-hand side and this ky, or the y part over to this left-hand side. This gives me dy over y equals k dt. Then I can just do integration of both sides. I end up with the natural log of y is equal to kt plus c. This constant must be here, right? We're taking an indefinite integral, so I don't get to remove that constant. This is our constant of integration. I can combine the constant of integration for both sides into one constant because one constant minus another constant is just a constant. Right? And this gives me a final functional form of y as a function of t is equal to e to the kt plus c, right? Because I've, to get rid of this natural log, I take the exponential of it. And then because of the rules of exponentiation, this is equal to some constant times e to the kt. Okay, and so notice that we end up with a family of solutions. I have a constant e to the kt, right? I don't know what this constant is. So it could be 3, it could be 7, it could be negative 236, whatever. I have this whole family that's going to follow this behavior of this exponential of kt multiplied by that c. So how do we solve that? Well, we need one additional piece of information. So in general, we will be given, in addition, if we want to find a specific solution in this family, we will be given some additional piece of information, such as y at t equals some constant is a specific value. For example, y at t equals 0 is 5. So given this set, I can go through, I can substitute this information into this equation. So that value is equal to c times e to the ka. I rearrange and I get c is that value divided by e to the ka, and then I know what c is. So in our example, if y is equal to y at t equals 0 is 5, I have 5 equals c e to the k times 0. That means c is 5. That means our final equation is y of t is equal to 5 e to the kt. Okay. These solutions represent our simplest functional form, right? I can do this with y, I can do this with t. I separate, I integrate, and then I solve for my constant. Things are a little bit trickier when I move to linear ODEs. So let's take a look in how we can solve that. So let's have our dy dt plus some arbitrary function of t, we'll call that p of t, times y, right, remaining linear in y, equals some function of t where y doesn't exist. So the goal is that we're going to convert this into something that is separable using an integrating factor. So our integrating factor we're going to call mu, which will be a function of our independent variable, and it's going to be equal to e raised to the power of the integral of that p function with respect to t. I know it sounds weird, but this is going to really help us simplify our solution. Okay, so before we go much farther, I want to make a quick note about mu of t. So this is why this is going to help us solve these problems. So if I take the derivative of mu with respect to t, I have the derivative with respect to t of mu. Okay, I can substitute mu in there. I get d dt of e to the integral of p of t. And that's equal, right, when I take the derivative of this, right, when I take the derivative of an exponential, I get the exponential back. So I get e to the derivative of p of t dt times the derivative of what's in the exponential. The derivative of an integral is the function itself. So I end up with p of t times e to the integral of p of t dt. Well, this is just mu of t again. So this derivative of mu of t is equal to p of t times mu of t. Okay, so let's see how we can use this information. I'm going to put that integrating factor and the derivative up here in the upper right-hand side of the screen, so we have that available to us. Okay, so what I'm going to do is I'm going to multiply through by our integrating factor. I have mu of t dy dt plus mu of t times p of t times y equals mu of t times q of t. Now, if you notice something interesting here, you'll see that this is equal to the derivative with respect to time of mu of t times y on this left-hand side. This is because the derivative of mu of t times y, right, by the product rule, is mu of t times the derivative of y, so mu of t dy dt, plus y times the derivative of mu, so y times d mu dt. And so if I look at that, that's exactly equal when I substitute in what d mu of dt is, right? So d mu of dt is p of t times mu of t. So that means this term is equal to mu of t, p of t, y of t, right? So in total, this derivative with respect to time of mu of t times y is mu of t dy dt plus mu t p of t y, right? So that whole piece up here collapses down. Okay, so now I can integrate this functional form. So I have the integral of d mu of t times y equals the integral of mu of t times q of t dt. When I do this integration, here's that equation that we've come up with. When I do that integration, the integral cancels out this derivative form. I'm left with mu of t of y equals the integral of mu of t times q of t dt plus that constant of integration, which came from this side over here. Now, all it is left is for me to solve for y. So y of t equals 1 over mu of t times the integral of mu of t times q of t dt plus c. So, so this is our final solution, and then I just need to solve out this equation. Okay, let's look at an example. So let's look at dy dt equals, dy dt plus 2y equals 6t. We know that this is a linear first order ODE because I only have one derivative, and I have y sitting here, and I can't do my separation. So let's identify P of t and Q of t, right? What's in front of my y? Well, that's a 2. What is Q of t? What's on the other side? That's 6t. Okay, so I now need to find my integration term. So remember, mu of t is e to the integral of p of t dt. So I can pop in p of t. So therefore, mu of t is equal to e to the integral of 2 dt. That leaves me with mu being equal to e to the 2t. I can now solve for y by substituting into that equation that I showed before. So y of t is 1 over e to the 2t times the integral of 6t times e to the 2t dt plus c. I can take this, multiply it through. I'm left with e to the minus 2t times the integral of 6t times e to the 2t dt plus c to the c times e to the negative 2t. We can now employ integration by parts to solve out this, to find the constant, to find the equation form of this integral piece. Using integration by parts, we end up with 3t e to the 2t minus 2/3 e to the 2t. Okay, so here we have that integral set. I can now plug in the solution to this integral from our integration by parts, and I'm left with y y to t. Y of t is e to the minus 2t times 3t e to the 2t minus 2/3 e to the 2t plus c e to the minus 2t. And when I multiply this through, I'm left with y of t is equal to 3t minus 2/3 plus c to the constant e to the minus 2t. Okay, so what did we do? We went through, we calculated, we identified our functions p and q. We found our our integration factor. We multiplied through. We substituted that into our equation. We solved this integral using, in this case, integration by parts, and then it just became an algebraic problem to clean this up to arrive at our final form. Once again, we have a single constant, which represents our that family of solutions. Okay, let's move beyond nonlinear first-order ODEs. There are 4 different types of nonlinear first-order ODEs. We have separable forms. So this would be dy dt equals some function of y times some function of t. So these can be nonlinear, but they have to be multiplied together, and you have to be able to separate them, right? So we can take, in this case, y, move it over here, dt, move it over here, and then I have everything on either the left or the right-hand side. All my y terms end up on the left, all my t terms end up on the right, right? And so then I just use a separate and integrate strategy. Similarly, I can have a homogeneous nonlinear first order equation, right? So dy dt equals sine of y, or dy dt equals 1 over t, right? Again, I can separate these. I can take my t, move it over to the right-hand side. I can take all my y terms, move them over to the left-hand side, and integrate just like we did with that first simple problem. Okay, so we can also have what we call Bernoulli type functional form. In this case, we have dy dt equals p of t times y equals q of t times y to the n. And this is important that I have to have on the right-hand side just y to the n. I can't have these extra terms. If I'm in this very special functional form, I can still solve it using a substitution of u equals y to the 1 minus n. And I'll show you this in a second. We can also have just general nonlinear functional forms, which are anything else. And these often require advanced numerical or advanced qualitative analysis to solve. We're not going to go into this today, into the advanced qualitative analysis, but I will show you later a simple numerical approach to solving this. Okay, let's take a look at solving the Bernoulli type ODEs, because these separable and the homogeneous forms are going to follow what I've sort of shown you already. Okay, let's look at these at our Bernoulli type equations. We have dy dt plus p of ty equals q of t y to the n. How I'm going to go about solving this is dividing through by y to the n. This will give me y to the minus n dy dt plus p of t y to the minus n plus 1 equals q of t. I'm then going to substitute in u equals y to the 1 minus n. When I do this, I can now solve through in terms of dy dt, du dt, right? I can solve this out because du dt equals negative y to the 1 minus n plus 1 dy dt using my rules of using the chain rule. I can take this information, I can substitute it in up here and solve. Let's look at an example. Here I have dy dt plus y equals y squared, right? I have a linear term in y, and then I have on the right-hand side, I have an equation that's have only a single y to this exponent. This exponent is 2, so my n is 2. Therefore, I need to divide through this equation by y to the n, or y squared in this case. And this will give me y to the minus 2 dy dt plus y to the minus 1 equals 1. Okay, so I now substitute in u equals y to the minus 1, right? I take 1 off of that exponent and determine my derivative of u with respect to t. So du dt is equal to minus y to the minus 2 dy dt, because the derivative of y to the minus 1 with respect to time is minus y to the minus 2. Okay, now I substitute this into this equation, and we'll see, right, that this term pops up here. I have my u, which pops up, my minus y to the minus 1, which shows up over here. I can substitute in to get minus du dt plus u equals 1. Now, all of a sudden, I know how to solve this because I now have a linear equation. Okay, so what I've done so far is we've taken our Bernoulli nonlinear equation. I've used a substitution factor of u equals y to the minus 1 to get minus du dt plus u equals 1. And then I can solve my linear ODE of du dt minus u equals minus 1. How do I solve this? This is now a linear equation. I'm going to solve this using an integrating factor like we just previously saw. I have my p of t, right? So what's sitting in front of the linear term? Well, that's minus 1. What's sitting in front of the nonlinear term? Well, that's also minus 1. So I can solve out my integrating factor of mu of t equals e to the integral of minus 1 dt. Well, that's easy. That's just e to the minus t. I take my linear ODE. I multiply through by my integrating factor to get e to the minus t du dt minus e to the minus tu equals minus e to the minus t. I'm following my procedure. I wrap this up into this d dt of e to the minus tu is equal to minus e to the minus t mu. I can solve this now by multiplying both sides by dt and integrating. So in the end, I get e to the minus t u is equal to the integral of minus e to the minus t dt. Once again, this is a relatively simple antiderivative that I need to take. This leaves me with e to the minus t plus our constant. So to find u, I just need to divide through by e to the minus t. So that gives me u equals 1 plus c e to the t. Now I have an equation for u. I know how u and y are related. I can substitute back in to find that y to the minus 1 equals 1 plus c e to the t. I invert this and end up getting y equals 1 over 1 plus c e to the t. All right, now that we've covered and with that, we've covered all of the methods that we're going to be covering to solve first order ODEs. Let's now investigate second order ODEs, which have constant coefficients. So for example, we're going to look at functional forms of a d squared y dy squared plus b dy dt plus cy equals some function of t. Within this, we're going to solve these analytically functional forms where both b and c equals 0, or this term on the right-hand side equals 0. Okay, so how are we going to do that? Let's look at a functional form when b and c are both 0. This is going to give us what we'll call our separable case. So when b and c are 0, we're left with a functional form of y times d squared y dt squared equals f of t. We can look at this and go, aha, I know how to solve this by separation. I multiply, I divide both sides by 1 over a, and I take out one of these d dt's, and I multiply the equation through by dt. This leaves me d, the derivative of y with respect to t equals 1 over a f of t times dt. I can solve this. We know how to do this. It's integration, a simple integration. I take my integral of both sides. I'm left with dy dt equals 1 over a, the integral of f of t dt plus a constant. Note here that I'm subscripting this and saying we have I'm going to call this C1 because we're going to have a C2 later when I deal with this second derivative. Okay, so here's that equation that we came up with. Let's just, for now, for this example, just assume that g of t is equal to the integral of f of t. Right, this is going to allow me to solve for this piece. So my final first derivative of y with respect to t is 1 over a g of t plus c1. Once again, I'm left with an equation where all my y terms are on the left, all of my t terms are on the right. I can move dt over to the right, integrate out to give me the integral of dy equals the integral of 1 over a g of t plus c1 dt. When I take this, I'm left with y equals 1 over a, the integral of g of t dt plus c1t, right? Because this c1 term gets its constant, gets its t, and then I have a second constant of integration C2. Okay, so let's do this. Let's look at what this might look like in an example. So let's say my second derivative of y with respect to t is sine of t. We're going to solve this by separation. I have d of dy dt equals sine of t dt, right? Because I've moved one of these dt's over to this side. I take my integral. This integral cancels out the d, leaving me at dy dt. The antiderivative of sine of t with respect to t is cosine t, so I'm left with dy dt equals minus cosine t plus c1. Okay, again, I can solve this by separation of the variables. I'm left with the integral of the derivative of y is equal to the integral of minus cosine t plus c1 dt. Y integrates out. The antiderivative of cosine is sine, so I'm left with a minus sine of t. I have to take the antiderivative of c1, so that's c of t, and then plus my second constant of integration, c2. Right? And so therefore, my second derivative of y with respect to t equaling sine t is solved by this functional form. I highly recommend that, of course, you take this functional form, and to just double check that that's true, you can now go in, take the second derivative of this functional form, and you should end up with that original starting case. Okay, let's look at what's called a homogeneous equation. This is when I have only terms that have these y's in there. There's no t's sitting by themselves. And these a, b's, and c's must be constant. So I have a d squared y dt squared plus b dy dt plus cy equals 0. We're going to solve this by assuming a solution. And that solution is going to have the form y of t equals e to some constant r of t. So this is going to be our assumption of what this form is going to look like. So if I go ahead and I take this assumed functional form and I substitute it into here, I first take the second derivative of ERT with respect to t, right? And I get ERT back twice times r twice, right? So I'm left with AR squared E to the RT plus B times the first derivative of e to the RT with respect to t. So that's r e to the RT plus c times y, which is e to the RT equals 0. I can remove e to the RT out, and I'm left with this second order polynomial, AR squared plus BR plus C. And when is this equation going to hold true? Well, this equation will hold true as long as AR squared plus BR plus C equals 0. Which we're going to call this our characteristic equation, because this equation will be true as long as this characteristic equation is equal to 0. Okay, how do we force this equation, this characteristic equation to be 0? Well, we can do that by finding the roots, right? So what are the roots that force this equation to be 0? There are 3 possible solutions to this. We can have roots where R1 is not equal to R2. We're not going to go into the method of how this is true, but when it is true that R1 does not equal R2, the final solution to this equation y of t is just the sum of those 2 pieces. So I end up with y of t equals c1 e to the r1t plus c2 e to the r2t.
I can also have a double root where R1 equals R2. This gives me this final functional form of C1 plus C2 times T times e to the RT. Or I can have a complex root where R equals some alpha plus or minus beta I. And when this is the case, my solution follows the form of y of t equals e to the alpha t times c1 cosine beta t plus c2 sine beta t. Let's do an example of second order ODE where I have that right-hand side being equal to 0. Here I have d squared y dt squared minus 6 dy dt plus 9y equals 0. I can pull out my characteristic equation, right? Okay, what is A? A is 1, so I have r squared minus 6. Okay, so that's B, so minus 6r. And then what's in front of y? It's just 9, so plus 9. So we have r squared minus 6r plus 9 equals 0. What do I need to do? Well, first I find the root. Okay, what does this look like? Well, using algebra approach, we can say that I have r minus 3 squared equals 0. Therefore, the root is 3. It's a doubled root. R1 equals R2. The root is 3. So therefore, my functional form is y of t equals c1 plus c2t e to the rt. And this can then be converted because we know that r is 3. I substitute r in here, and then I'm left with y of t equals c1 plus c2t e to the 3t. All right, let's talk about solving for the constants now that we've seen how to solve second order ODEs. We've seen that when solving second order ODEs, we have two constants which appear. Therefore, we need two pieces of information. And there's sort of two that are possible. This Dirichlet boundary condition, where we know a value at points. And these are sometimes called boundary value problems. For example, I need to know a value in space at two different points. So y at some t1 equals a, and y at some other t, so t2 equals b. So I know information about y at 2 points in space, and I therefore can solve for my two constants. I can also have a Neumann boundary condition where I know information about the derivative at a point in space. So I know information at a point in space, so y at t equals t1 equals a, and I know information about the derivative. The derivative of y at some point t2 equals b. And in this case, t2 may or may not be t1, right? So I can have them at the same point or at different points, and then I can move forward. Let's see this in practice. Let's assume that after I've solved my ODE, I'm left with y equals 1/2 x squared plus c1x plus c2. And I'm given the boundary condition y at x equals 0 equals 3, and y at x equals 1 equals 7. So by taking these two pieces of information, I can substitute them into this ODE and solve for my unknowns. So I have 3, right? So from this boundary condition, I have 3 equals 1/2 x squared, right? So 0 squared plus c1 times 0 plus c2. And then I know that y is 7 at x equals 1, so 7 equals 1/2 1 squared plus c1 times 1 plus c2. If I look at this piece, this equation up here, I'm left with 3 equals c2, and then I can substitute c2 is 3 into this equation and find out that 7 equals 1/2 plus c1 plus 3, so therefore C1 equals 3.5. So my final functional form is y equals 1/2 x squared plus 3.5x plus 3. Let's do the same thing, but using Neumann boundary conditions. Again, I have y equals 1/2 x squared plus c1x plus c2. I'm assuming that we're given that y at x equals 0 is 3, and that my first derivative at x equals 0 is 7. So we need to know my first derivative. Well, I can take my first derivative of y. As I go through here, I take the derivative of this piece, so that's equal to just x. I take the derivative of c1x, that's just c1. And then the derivative of c2 is 0. So this gives me the derivative of y is x plus c1. I still have two equations with two unknowns. I have 3 equals 1/2 times 0 squared plus c1 times 0 plus c2, and 7 equals 0 plus c1. This gives me a total equation of y equals 1/2 x squared plus 7x plus 3. Okay, so now we've covered how we can solve second order ODEs. We've talked about boundary value problems, and we've talked about initial value problems, and we've talked about how we can solve for this constants using information known at 2 points or knowing information about both a location in space and a derivative. However, many problems in chemical engineering are quite advanced and are difficult, and they may not have analytical solutions, right? We may not have a way to just take that differential equation and come up with a solution. Therefore, we need to use what's called an analytical approach. And the one that I'm going to talk about today is called Euler's method. Euler's method is going to convert this differential equation into something that we can solve by doing numerical sort of substitutions and solving it piece by piece. So I'd like you to remember the definition of a derivative. The definition of the derivative is dy dt is the limit as t goes to 0 of dy of some change in y with respect to t. What we're going to do is approximate this derivative not at the limit of y of t going to 0, but at some fixed t value. So we're going to say, sorry. So we're going to say that this change in y with respect to t is equal to that function that we're given. Okay, and so what is the change in y? Well, it's, y at some I plus 1 minus y of I. So I can rearrange this equation by moving delta t over to the right-hand side of the equation and leaving me with delta y here, where we have y I plus 1 equals yi plus dt times f of yt. I will link in the bottom of this lecture video I will put in the bottom of this lecture video a link to a fuller description of solving, taking numerical approaches in Euler's method. But let's do an example. So we're given, say, dy dt equals 3 plus t to the minus 1. And we know at the beginning that y at t equals 1 is 0. We're going to convert to this numerical form and select a step size. So let's say dt equals 0.5. In doing this conversion, I'm left with y at I plus 1 is equal to yi plus delta t times 3 plus t to the minus 1. We're going to solve that using this numeric table. So I'm going to start up, I'm going to make a column of t's and a column of y's. I know that at t of 1, y is 0. So first, I'm going to solve for f of t and y. So this f of t and y is, of course, 3 plus t to the minus 1. So I can substitute in my known t's and y's. So that gives me 3 plus t to the minus 1, so 1 to the minus 1. And that's equal to 4. I can now use this information to solve this equation here. So y I plus 1 equals my current y, which is 0, plus my time step, which is 0 0.5, times that functional form value, which is 4, which gives me, when I do this math out, I end up with y of I plus 1 equaling 2. Okay, now I'm ready to move down here. So what's my next time? Well, my next time is 1.5. My next y is 2. I can go ahead and again solve for my functional value at t equals 1.5, right? So I get 3 plus 1.5 to the minus 1. That leaves me at 3.66. I can solve for my next y. So y of I plus 1 is my current value of y, which is 2, plus 1/2 times 3.666, which is my functional function value, and that gives me 3.83333. Okay, so I want to note that, of course, numerical approaches are going to introduce error because I'm taking this step forward, and y should be changing continuously. This is inherent in doing a numerical approach. However, I can minimize this error by taking smaller and smaller time steps. So making dt instead of 0.5, make it 0.0001. This is going to minimize my error, but require a lot more computational power. I could, of course, use more advanced methods, which you can find in the playlist that I'll link at the bottom of this video. However, those are unnecessary and just there if you're curious. Okay, so now that that wraps up what I'm going to cover on solving ordinary differential equations. Hopefully you're now familiar with ODEs and PDEs. You can solve first order separable ODEs. You can solve linear first order ODEs. You're familiar with homogeneous second order ODEs, and we can solve initial value and boundary value problems. These have all been shown on how we can get analytical solutions. And then because we can't always use analytical methods, we sometimes have to use non-analytical methods or numerical methods, such as an exemplar, which is Euler's method. So please remember to take your comprehension check, and I will see you next time.